Okay, the recording has started. Good morning, everyone. Welcome back to Math 115. Sorry, I'm kind of just all out of sorts this morning, but we're going to power through. Today's class, we're going to talk about sections 1.6 and 1.7. So regarding that, I haven't posted a homework for 1.6 and 1.7 yet. We're going to talk about them today. Depending on how much I get through of 1.7, we might need a little bit of tomorrow to do some of that. There will be a homework coming on, not on 1.6, but just for 1.7. I'm combining the two, basically, into a single homework. So that is going to be what we are doing for homework. So 1.4 homework was already due yesterday, and 1.5 homework is due Wednesday, which is tomorrow. So 1.7 homework is coming soon. Your next assessment is going to be quiz 3, which will be this Thursday. So not tomorrow, but the day after tomorrow. And I have office hours today. So if you want to get a head start on studying for that quiz this Thursday to bring up your quiz average, maybe because you haven't had a couple of great quizzes for your first 2 quizzes and you're worried about not having enough dropped at the end of the semester, then I'd recommend coming to office hours today. So can I have a show of hands of who's planning on coming to office hours today? Okay, I might need to get a classroom. I'll email you all, and I'll put a note on my door if I move to a different room, okay? All right. Also, if you can't make it to office hours, the other best way to study for the quiz would be to go to LeConte 102. You don't have to bring anything. You don't have to sign up. You don't have to do anything other than just put your body inside of the room, LeConte 102, and someone will help you. Those are the ways that you can prepare for the next assessment. By the way, I just want to remind everyone. Let's see if I have the syllabus still on here. I do. I just want to remind everyone. No, that's not the syllabus. I just want to remind everyone that at the bottom of the syllabus, you can find the date of every single quiz and exam. And if you know when all of the dates are, then you will never miss a quiz or an exam. And yeah, you can just put them in your calendar now and have those available. So the quiz and exam schedule is at the bottom of the syllabus. Well, while I'm looking at the schedule, I might as well also inform you that we're a little bit behind. We're currently in week 5, which means this week we're supposed to do 2.1 through 2.4, but today we're finishing up 1.7, so we're probably like 2 days behind, but that's okay. Okay, back to chapter 1. I think that's all I had to say administrative-wise. Any questions on that before we started on content for today? Let me mark the other people present. Who came in while I was talking? Chris is here. Sarah? Lawson? Connor is here. Emma's here. Jada or Liv? Liam? Zane? Or Kayla? No? Okay, we're good. All right. So I guess let me start by reminding you all what we talked about last time, as is tradition. So last time we talked more about properties of functions. So the properties of functions which we studied were, of course, when is the function increasing or decreasing, i.e. if as we move from left to right, is it going, why did that happen? Is it going up or is it going down, right? That's increasing versus decreasing. Or is it going just straight ahead? That's constant. Then we also learned about how to express the locations where our functions are increasing or decreasing. And the takeaway there was we always use parentheses, okay, because we're never increasing or decreasing at just a point. We're always increasing or decreasing on an open interval, okay? Or a union of open intervals is also okay. Okay? All right. So next we talked about maxes and mins, okay? So peaks and valleys. So I gave a really technical definition, which I won't repeat now. Okay, how to find the maximum or the minimum of a quadratic depends on whether it opens up or opens down, but it's always going to be at the vertex, right? Okay, and then even and odd. Okay, so even and odd might have been the trickiest part of last lecture. It's how to tell if things are even or odd, and what we do is we check, for evenness, we check, is f of x equal to f of negative x? Okay, so the way you check that is by plug in x. That if you plug in x to the function, you just get the regular function. But if you plug in negative x, then you plug with parentheses, like so. For x squared, it would look like this. And then you would multiply that out, and we would get x squared. And you would see, aha, these two things are the same. And that's how you would check for evenness. To check for oddness, we do the same thing, except we also want it to be negative. Okay, we also want it to be negative. So even functions are symmetric about the y-axis, okay, meaning this way and that way. And odd functions are symmetric about the origin, meaning this way and that way. Okay, so we did a practice checking evenness and oddness. And then we talked about average rate of change. Now, what was average rate of change? Well, if we took a function over an interval from a to b, what we did was we said, well, if you look at the point a f of a and b f of b, and you draw a straight line between those two, well, the slope of this line is going to be the average slope of the curve, okay? So sometimes this curve is going a little steeper than that slope, but sometimes this curve is going a little less steep than that slope, right? So you can imagine if you drew like 100 dots all on here, and you did one of these arrows like that for all of them, right, to kind of describe the steepness of how steep we are at a given point on this guy. And if you averaged all of them from here to here, then the average slope would be the slope of this direct path, okay? So another word we call this, another word we use for this line is called the secant line. A secant line is basically a line that touches our mathematical object at 2 points. It basically, it cuts off a piece of it, right? You imagine if this was a knife, I would slice here and I'd get this little piece of apple or something like that. So that's a secant line. All right, and then we did an example of that. So quite a bit of material that we covered last class. Today we're going to again cover quite a bit of material. Are there any questions on what we talked about last time? Or anything that you encountered in the homework that was really confusing? All right, well, maybe you can look it up for me and give it to me later. Okay, doesn't seem like there's any other questions other than the one pending. So let's start in on content for today. So what we are going to talk about in 1.6 and 1.7 is building up a library of functions, okay? A library of types of functions, and also their graphs. And also their graphs. And what are we going to do with this library of functions? Well, in 1.7, we're going to learn how to stretch them, how to move them, how to, yeah, I guess that's it. Stretch them and move them is what we're going to, oh, and reflect them, right? Okay, so we're going to learn about function transformations. All right, so before we can learn about function transformations, let's get down, it's going to be super useful to have down the basic family of common functions so that you know, okay, the graph of a common function looks like this, and if I want to stretch it, well, what is it going to look like if I take that function and I stretch it, right? Okay, so the first ones to talk about, we've already discussed, I think, at length, are linear functions. Okay, so linear functions have the form ax plus b, where a and b are real numbers. So this is lines, right? So 2x plus 3, or negative 2x plus 3, right? Or f of x equals 0 would be a constant, right? So all of these things are linear functions. And what do their graphs look like? Well, they look like lines. All right. So that one I'm going to confidently move past. The square root function. Okay, of course, remember, every time we talk about the square root function, okay, or if I write f of x equals to square root x, then it is implied. It is implied that we're discussing the principal square root, okay, namely only the positive one. Why is that important? Can anyone answer that question for me? Why is it important? Yeah, Sully.
Because if you include the negative one too, it would pass the vertical line test.
Exactly. Sully's hit the nail on the head. If you included the negative one too, then what would our function look like? It would look like this. And why is that a problem? Sully also answered that for us, because it's not going to pass the vertical line test, right? If I put this vertical line, it touches at this point and at this point, right? So that's 2 points. I need to have only 1 point touching my vertical line. Okay, so in other words, it wouldn't be a function, it'd be a relation. So if I say function, it's implied that we're only talking about the positive one, because if we were also including the negative one, well, it wouldn't be a function, okay? All right, so square root function, or if I write f of x, that also means we're talking about a function, okay? All right, so what does it look like? Well, we're just going to draw the positive part of the square root. It looks like this. It looks like 1/2 of a parabola. All right, pretty simple. All right, so now let's do something more complicated and talk about the graph of a cube root function. Okay, let's talk about the cube root function. Now, let me ask you all a question. Is it important that I only take the positive cube root? No, why not?
Because it's not going to come out with an issue with a positive power.
Exactly. So, okay, the problem, or the lack of problem, comes from the fact that the cube root of 2, or let's take a look at the cube root of 8, right? What is the cube root of 8? It's 2. Okay, when we're doing square roots, you also get a negative root, right? But what happens if I do the, I mean, is it true that the cube root of 8 could also be negative 2? No, because if you did negative 2 times negative 2 times negative 2, what would you get? Negative 8. Okay, so not only is it not a problem that I'm not taking the positive root here, it's also not going to be a problem for me to put in a negative number, is it? Right? Negative roots can, or roots of negative numbers can always be done as long as your root is what? Odd. Which 3 is odd. Okay, so this one is going to look like a lot like the square root, except it'll look a little bit flatter, I guess, than the square root. I don't know if that's clear from my drawing. Okay, let's zoom in and maybe make this a little more clear. Okay, so it's a little bit flatter, meaning square root would look more like this. Okay, but then what else? We're also going to have a negative part. What's it going to look like on the left-hand side? Yeah, it's going to look like this, but down here, right? Okay, by the way, the properties of functions that we talked about last time. Does this remind you of any of those properties? What kind of function is the cube root of x? Sorry?
Origin?
I just didn't hear what you said the first time.
Symmetric.
Yeah, it's symmetric about the origin. What kind of functions are always symmetric about the origin?
Odd functions.
Odd functions. Very good. Okay, so it's an odd function. So that's just a tie-in from last time. All right, let's talk about piecewise functions. Well, how do we define piecewise functions? Man, I really left myself a lot of leeway here to just write something down. Okay, well, for f of x is a piecewise function. What we do is we write f of x equals, and then we do one of those big braces. Okay, it's going to be bad, but that's actually pretty good. Okay, so we do one of these big braces, and then what do? We write basically the rule, and then when the rule applies. Okay, so for example, I could do f of x equals x if x is larger than or equal to 1. And we can also do like a triple piecewise. Let's do a triple piecewise just for fun. F of x is also going to be equal to 1 if x is bigger than 1. No, I don't want bigger than 1. I want bigger than 0 and smaller than 1. And then f of x equals maybe negative x minus 1 if x is less than or equal to 0. Okay, so what have I done? I've basically partitioned the domain. Okay, so I've got the domain here, and I've got 0 and 1. Okay, and basically what I've said is I've partitioned the domain. So this is the part where x is larger than or equal to 1. This is the part where x is between 0 and 1. And then this is the part where x is less than or equal to 0. And for each of these parts of the domain, I've assigned a different rule, okay, which is going to be, okay, when I'm at an x value which is larger than 1, this is the rule I'm going to use. When I'm at an x value that's between 0 and 1, this is the function rule I'm going to use, and so on and so forth, right? So what would the graph of this one look like? Well, I just need 1 and also 0. Okay, so if x is bigger than 1, what's the function height going to be? It's going to be whatever x is, okay? So if x is at 1, I'm going to apply this rule because we've got the larger than or equal to, right? So if x is at 1, the function height is 1, right? And I'm going to put a closed dot because greater than or equal to. And then from there, what is going to happen? Well, if I go over to 2, I'm still going to apply this rule. And this rule says make the height equal to whatever the x value is. Okay, so it's just going to look like the line y equals x, where we are going up by 1 over 1, up 1 over 1. Okay. How about in this region, from 0 to 1, what will the graph look like? Yeah, 1. I guess I'm looking for a more descriptive term than 1. What kind of function is f of x equals 1? Is it an increasing function? It's a constant function, right? Okay, because it's equal to a constant, and also it doesn't change, right? So it's constant in both senses. So I'm going to put an open dot here, right? Because that's where it would be if I were to be able to plug in 0 for this rule, but I can't because I have a less than. And then I'm going to draw a line, and then I would draw an open dot here, but I don't need to draw an open dot there because there's already because there's already a closed dot from the other rule, so I don't need to draw an open dot. Okay, so that's 2 pieces done. Now let's do the last piece. This is going to be how I draw the graph when the x value lies on the negative x-axis. So what does the function negative x minus 1 look like? Let's use some of our descriptive terms. Is it increasing, decreasing, or constant? Why is it decreasing? Because the slope is negative, right? Slope is negative. Therefore, it is a decreasing function, right? And the y-intercept is negative 1, right? So we know that if x was equal to 0, then what is this function going to take the value of? It's going to take negative 1 as a value. So here's negative 1. And am I going to put a closed dot or an open dot? I'm going to put a closed dot because I have a less than or equal to sign, right? Okay, so for that reason, I'm going to put a closed dot because the rule does apply when x is equal to 0, right? The rule does apply. So I'm going to put a closed dot at negative 1. And then I'm going to draw what looks like a negative slope line. And it also passes through the point negative 1, 0, right? Because the slope is 1. Negative 1, excuse me. Okay, so that's how we draw a piecewise function. So in my experience, a lot of students struggle with this, but it helps if you visualize it like this, right? We have the rule, and then we have when is that rule going to apply? Okay? Any questions so far on piecewise functions, cube root, square root, linear? All right, let's do something more interesting then. Let's talk about step functions. It's possible you've never heard of step functions before. Oh, let's have a show of hands. Who's heard of step functions before? Okay, some of us, but not very many. Okay, so let's see why they call them step functions. Well, other than drawing the graph, I'm not really sure how I'm gonna discuss this. So, okay, an example of a step function would be the floor function. F of x equals to x. Okay, and this is called the floor function. And the floor function is really useful, actually, especially in programming. So can anyone tell me what the floor function does, if you've seen it before? Okay, it doesn't seem like anyone's seen it before, so that's good. All right, well, the floor function basically does the following. It maps x to the largest integer less than x. The largest integer less than x. Okay, so for example, 3 goes to 3, but 3.5 also goes to 3. 3.9 also goes to 3. Okay, so it's kind of like rounding. Actually, it's more like I'm just going to take whatever is the decimal part and get rid of it. Okay, that's what we do. And then something like 4.1 would go, of course, to 4, right? So what does it look like? Well, if I talk about 1, 2, 3, right? What is this going to do? It's going to, for every number which is less than 1, it's going to map it to 0, right? So I'm going to get mapped to 0. And then if I'm at 1, what am I going to map to? I'm going to map to the largest, okay, I should have said the largest integer less than or equal to x. And if we're at 1, then we're going to get 1. And then if I plug in something like 1.1, 1.2, 1.3, 1.4, 1.5, I'm going to always get 1, right? And then I get another open dot, and then we go up to 2, and we just repeat this process. Okay, so that's step functions, or this is an example of a step function. You could have the steps go only like this if you wanted, or something like this. That would also be a step function. But the point is, it looks like steps, right? If I was here and I was walking from left to right, what would I be doing? I'd be going up or down steps. So that's why we call them step functions. All right. Any questions on step functions or the floor function? Okay, so maybe I'll explain why the floor function could be useful. Let's say you have a quantity which you want to measure which only takes discrete values, meaning it only takes values like 1, 2, 3, 4, 5, right? But there's also a sense in which it takes continuous values. So what would be an example of that? Something would be like number of years alive, right? If I'm talking about the number of years that I've been alive, it's something like 27.1, right? But if I want to tell you my age, what am I going to tell you? I'm going to tell you 27. I'm not going to say I'm 27 and 0.1, right? I mean, maybe if I'm like 4, then I'd say I'm 4.5, right? But if I'm older than that, I'm probably just going to give you the whole number, which is the largest integer less than my actual age, right? So that's an example of like a situation where maybe if you were programming something, right, and you had this big database of like people and their ages and all of this stuff, you might want to just use their age to the nearest year, but round it down, right? Bug. Okay. All right. Let's. Okay. So no functions on, or no questions on step functions. All right. Let's talk about function celebrities. Okay. So what am I trying to communicate here is that you need to know the graph of all of these functions off the top of your head? Okay, so this would be a great opportunity to make some flashcards to help you remember what all of these look like. Okay, because having an understanding of what all these look like is going to be super important for the next section when we talk about how to stretch, move them up and down, move them left and right, and also flip-flop them back and forth, or up and down, or, every which way, okay? All right, so let's go through them one by one. First of all, it's the constant function. What does it look like? It looks like a constant. It doesn't change its height at all, okay? You could also say that this is a horizontal line, right? Okay, and also for your benefit, they include the domain, range, and evenness versus oddness, if it applies. Okay, then we have the identity function. That's another name for f of x equals x, or y equals x, or the line with slope 1 and intercept 0. Okay, so it goes up. It's an increasing function, and that's what the graph looks like. Okay, the squaring function. I never have ever heard in my life someone call it that, but that's what I guess they call it. It's f of x equals x squared. It's a parabola. You know it well. It comes down, it touches 0, and then it goes up, right? So it's decreasing until we get to 0, and then thereafter it is increasing. And it's an even function. Why is it an even function? Well, I guess it's already written here, isn't it? It's an even function because it's symmetric about the y-axis, right? Okay. Next up is the cubing function, okay? So the cube root, or not the cube root function, but the cube function, of course, looks like this thing. It looks kind of like, if you want to remember how to draw it nicely, you can start at the origin and draw half a parabola this way, and then start at the origin and draw half a parabola this way. That'll help you to draw it. And of course, it's an odd function. Why is it an odd function? Because it's a power function, and the power is odd. All right. How about the absolute value function? Okay, of course, you remember what the absolute value function does. It maps, let's see if I can get a black pen here. It maps x to x if x is positive, and it maps x to negative x if x is negative, right? So when x is negative 2, the absolute value is 2. When x is 2, the absolute value is 2. So, of course, it's also going to be an even function. And it just looks like this v, basically. All right. Next up is the square root function. Okay, we already saw this one. The principal square root is implied because we already described that it's a function. The only type of square root that is a function is the principal square root. Okay, so it's not even or odd. Why not? Why is it not even or odd? Yeah, I mean, there's not even a left-hand side. How are we going to say that it's the same on the left-hand side and the right-hand side? It doesn't make any sense, right? Okay. Oh yeah, there's more. Okay, so next up is the cube root function. Okay, what does cube root look like? We already drew it today, in fact. It looks like this guy on the right-hand side, and then you draw the same thing on the left-hand side, and there you go. It's like a square root, but a little bit lower. Okay, so if you wanted to draw a square root, it would look maybe more like this. Okay, so that's the cube root function. And of course, it also is an odd function. So even though the cube root is an odd function, it's kind of interesting. The square root is not an even function, right? Okay, so just because there's a 2 here and that's an even number doesn't necessarily mean this is an even function, right? We have to be a little bit careful. All right, so next up is the reciprocal function, which, again, I don't think I have ever heard people call it the reciprocal function, but f of x equals 1 over x looks like this. Why? Because when you divide by something which is close to 0, okay, if you divide by a fraction, if you divide by, like, say, 1 over 100, that's the same as multiplying by 100, right? So that's why it gets really big when the denominator gets really close to 0. And of course, if the denominator is negative and really close to 0, then we're getting really big and negative. Okay, so this is an odd function because if you take a point here, there's another point on the opposite side which matches it. Okay, actually not that. I should have done from here to here, right? You draw a line through the origin and you match another point on the other side, something like this, okay? All right. And then we also have the reciprocal square function. Why does this one look like this? And when I do 1 over x, it looks like this. Why is it so different?
Because square negative becomes positive.
Exactly. When I talk about this guy, okay, this is -1. When I plug in -1 here, I get a negative number. When I plug in -1 here, I would get 1 over -1 squared, which would just be 1. Okay, so it just makes this part come to the top. Okay, but also it does more than that. It's hard to tell, but it's also steeper. Can you tell that it's steeper? It's steeper here than it is here. Okay, so just look at where we're at 4. We're like almost at 0 when x is 4. When x is 4 on this guy, we still got a little space, right? That's because when x is 4, this one would be 1 over 4, and this one would be 1 over 16, right? Okay, so it also decreases a lot faster. All right. So we're going through these really fast. Let's stop and ask. I think these 3 are probably super familiar to you. These ones you should have seen before at least. And these ones are getting into the territory of being more confusing. So how do we feel about these so far? Are there any questions? Okay. Then let's talk about the last couple of ones, which maybe you probably haven't seen. Okay, so the greatest integer function, also known as the floor function. So I already drew that one. Okay, what do we have? Okay, x to the 3 halves. Okay, so how do we do something like a rational power function? Well, it depends. It depends basically on one thing. It depends whether the power is bigger than 1 or smaller than 1. Okay, so in this case, the power is 3 halves, which is larger than 1. And in this case, the power is 2/3, which is less than 1. Okay? So if it's less than 1, it's going to take the shape of like a square root. Okay, it's going to take the shape of a square root. All right? And then if we are larger than 1, it's going to take the shape of like a half a parabola, right? Half a parabola, something like that. Okay, so one thing that we do want to be careful about is, okay, you know what? I don't think that's important for where you're at in math right now, so I'm not gonna go into that, and because I feel like it would be too confusing. For now, I will just say it's possible sometimes that this will also have this, and it's possible sometimes that this will not have this. It depends on whether this root is an odd or an even root, but for now, I'll say I'll never test you on that. If I ask you to draw something like this, I'll specify what the domain is. Deal? Okay. All right. So those are the last 3. Any questions on those ones? What are you trying to see, Griffin? Can I zoom in for you? Is that better?
Yeah.
Okay. All right. So that's our library of functions. So I would recommend that you make a flashcard for each of these. On one side, you could put this information. Well, okay, you could put this information and also, of course, the function itself. And then on the other side, you could put the graph. And I think that you should study those front to back and also back to front. And that will help you to get a baseline understanding of these functions so that when it comes up on the exam and I say something like, please graph x minus 1 cubed plus 3 and all negative, okay, you have a baseline understanding of, okay, well, I know the x cubed function looks like this, and I know what all of these transformations do, okay, and so I'm going to be able to confidently graph that without a calculator, without the internet, without Desmos, or anything, right? So that's the goal. So in order to achieve that, I think it's really important to know what the x cubed function looks like to begin with, or else how are you going to go about stretching, reflecting, translating it, right? Okay. So that's my spiel on the library functions. So that's all the functions that we need to worry about for now. We're going to learn more functions later in the class. But what I want to talk about now is what I was just saying, which is we want to learn how to move them around, flip them every which way, and do all sorts of crazy stuff to them. Okay, and the math word we use for that is transformations. Okay, so like I said, the idea is going to be we want to memorize the graphs of a few functions and then learn how to shrink, stretch, translate, and flip them. Okay, so, you wouldn't want to say memorize the graph of x cubed and also the graph of x minus 2 cubed and also memorize the graph of x minus 1 cubed and do this for every number that you could possibly plug in, right? All we are going to do is we're going to memorize the graph of x cubed, and we're going to learn what it does to the graph when we do something like this with a minus sign in here, right? We're going to learn what it does to the graph when we modify this equation a little bit. And if we learn a basic library of functions and how to transform them, we'll be able to graph a massive amount of functions all together. Okay, so that's the goal. So let's talk about the first and easiest transformation that you can possibly do, which is called a vertical shift, okay? Or the other word that I'll use interchangeably with shift is translation. Okay, translation is what I will also use. So the graph of f of x, okay, is going to be shifted up if we do the following. We take the function, and all we do is add a number to it, okay? So this will be like a new function, okay? So we could say g of x is equal to f of x, and then we add a number, okay? So if you had a graph of f of x, okay, what does it mean if I add a number to the output? It means that the height is going to be increased by that number for every single point on the graph, right? So what is this going to do? We're going to move up a. We're going to move up a. We're going to move up a, no matter where we are, right? That is how we're going to get the new graph, which would look something like this, right? Okay, so this is the goal of the vertical shift. So f of x plus a, we shift it up a units. Okay, one more thing I need to discuss is you can see I put these quotation marks around up, okay? The reason that I put the quotation marks around up is because if a is a negative number, right, then what am I going to do? I'm going to shift up by a negative amount. What does it mean if I go up by a negative amount, really? It means I'm going down, right? Okay, so let's do three examples, I guess. Well, two, I guess. So, okay. Remember, what does the graph of the absolute value function look like? We just learned that. Looks like what? A V. Very good. So let's draw it. Maybe it looks something like this. And by the way, what is the slope of this part of the line? Or of the graph? Is there a way to tell what the slope of this part of the graph is? Well, we can tell what the slope of it is because we can define the absolute value function as a piecewise function. Absolute value of x equals x if x is positive, and negative x if x is negative, right? So what is the slope of the function y equals x? The slope of the function y equals x is 1, right? So that is the function rule that we use when we're on the right-hand side of the x-axis. The function rule that we use on the left-hand side is negative x. What's the slope of this part going to be then? Negative 1, right? Okay, and what if I put like a 3 here? If I put a 3 here, then it would just be steeper, right? And then this side would be 3, and this side would be negative 3 in terms of the slope, right? Okay. So let's see how this is going to change when we do a vertical shift. All right, so if I do f of x plus 3, okay, if I do f of x plus 3, then what this means is for every point on the graph, say, for example, I could look at the point here, which is, of course, the point 1, 1, right? What am I going to do to this point? I'm going to move it up by 3, which means I'm going to add 3 to the y component, right? So instead of starting at 0, I'm going to start at 3, and I'm going to look like the same, because I'm not stretching at all. It's going to look exactly the same. And then what is the point going to be when the x value is 1? It's going to be 1, comma, what? 4, right? Because I add 3 to the y component. So I get 1, comma 4. Okay, so I do that for every single point on this graph. Okay, so all of these points and all of these points, I just take the y value and I add 3. All right, so let's see what happens if I do f of x minus 2. Well, I'm going to go up by negative 2, right? I'm going to go up by negative 2. That means I'm going down 2, right? So it's going to look like shown, where we start at negative 2. And what are the coordinates of this point here? Something, comma, something. If this one's negative 2, 0, what are the coordinates of this point here? They are going to be 2, 0, right? Why? Because we move over 1, up 1, over 1, up 1. If we want to go up by 2 units, we have to go over by 2 units, right? All right. So this is how we do a vertical shift. So that's, like I said, I think the easiest one that we can possibly do. Do we have any questions on that one? I feel like I shouldn't lead the question asking by saying that this is the easiest one. It's not easy. It's just that these are going to get more complicated. So without saying that it's easy, are there any questions on this one about how we accomplish this? All right. Doesn't seem like it. So let's move on to horizontal shifts. Okay, and you're going to notice that there's something really, 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 really annoying about how everything's nice when we're doing vertical things. But when we're doing horizontal transformations, everything feels really unintuitive, okay? And here's why. If we add by a number on the inside, okay, well, first of all, adding by a number on the inside as opposed to on the outside, like shown, if we add on the inside of the parentheses, this is going to produce a horizontal shift. So that doesn't seem so confusing. What's confusing? Well, if we add a number, we shift left by that many units. Okay, so why is that confusing? That's confusing because when we add a number on the y-axis, we go up. It feels like if I added a number here, I should go to the right, but I don't. I actually go the opposite direction. Okay, so what I recommend students to remember about horizontal transformations is you don't have to remember the rule. What you need to remember is that the rule is the opposite of what you think it would be. And I feel like if you remember that, it will help you to remember which direction to go. Okay, so let's see how this works. So if I have f of x equals x cubed, well, how would I go about drawing the graph of x cubed? What would be a good process for that? Half of a parabola, very good. On this side, oops, that's not a very good one. Half of a parabola on this side and half of a parabola on the other side. Okay, it looks something like this, right? Okay, so what am I going to do when I subtract by 1? Am I going to go to the left or to the right? I'm going to go to the right. Here's why. If I add a number, I go to the left by a units. Okay? And x minus 1 cubed is kind of like x plus negative 1, all cubed, right? So I'm going to go to the left by negative 1 units. If I go negative 1 units to the left, that's the same as going 1 unit to the right. So I'm going to move this entire graph over to the right by 1. Okay? And it's going to look like shown. Okay, so what did we do? We're at the origin first, but now we moved it to the right 1 unit. All right, so what's going to happen to us when we do x plus 3 cubed? Are we going to move to the left or to the right? Sorry? To the left or to the right? I'm going to move to the left because we're adding a number. Okay, see, it's so confusing when we're doing this on the inside. It's kind of backwards. Do you agree with me, by the way, that it's confusing?
Yes.
Yeah, it feels like so wrong, but that's how it is. We move to the left by 3. So here's 1, here's 2, here's 3. And then we have a graph which looks like this. Okay, so how do we feel about horizontal shifting?
I don't like it.
It's all right. We love it. Yeah, horizontal shifts.
Okay, maybe we should all just take a deep breath before we move on, because it gets worse. Okay, so like I said, my biggest advice with the horizontal transformations is just remember it's the opposite of what you think it should be. And that will serve you well not just for horizontal shifts, but also for horizontal stretches and compressions, which we're about to see. Okay, are we ready to move on here? Oh, okay, never mind. We have a combined 1 and 2. Okay, so yeah, we can do both. It's fine. We can do both. Nobody panic. I'm definitely not panicking. Okay, so what does this mean? Well, let's handle it piece by piece. I know when I subtract something on the outside, what effect is this going to have? It's going to be a vertical shift down 3, right? And what about this one? If I add 2 on the inside, that's going to be a horizontal shift. Which direction? Left. 2. Okay, so I start with the graph of the, where is it? I start with the graph of the square root function, which looks like shown. And then what are we going to do with it?
Move it down and to the
we're going to move it down 3 and then to the left 2. Are you okay?
Yeah.
Okay. Are you sure?
Yeah.
Okay. All right. So what are we going to do here? Let's move it down 3. 1, 2, 3. So that's minus 3. And then we've got 1, 2. That's minus 1, minus 2 to the left. Okay, so I'm just going to redraw this graph. It's not going to have a dot. Oops. It's not going to have a dot there. Okay, let's see if I can just barely finagle that. There we go. All right, so it's going to start right down here, right? And it's going to go something like this, okay? Going to go something like that. Okay, so what is this point going to be? Where is it going to cross the x-axis? Well, I know I need to go up 2. If I need to go up by, no, sorry, I need to go up by 3, right? If I need to go up by 3, then I need to move over how many? I think I need to move over 9. Right? Okay. Okay, so here's how the square root function looks like. Okay, let's remember what the square root function does. Okay, at 1, the square root of 1 is 1, right? And then we have to go over to 4. The square root of 4 is 2. And then the square root of, and then I go all the way to 9, right? And the square root of 9 is 3. So to go up 3, I need to go over by the square of that number. So yeah, I didn't draw the picture very well. It kind of looks like it's gonna pass through there. Really, I should have drawn it better. It's gonna look more like it's gonna pass through the point what? 7, 0, right? So here's 7, 0. And the square root function will look something like this. Okay, so that's a better drawing. I probably confused you by drawing it like that. Okay, so this is how inputs work with the square root function. That was really funny, though. When I was like, I said 9, I felt like there was a sudden outburst in the class. All right, well, that is a tricky example. But what's important to remember is, okay, what is the shape of the graph? And I'm going to move it over a certain amount according to what I add or subtract on the inside, and I'm going to move it up and down a certain amount according to what I add or subtract on the outside. Okay? So that's a combination problem. Any questions on this problem? Or any steps you'd like me to repeat or go into further depth on?
Could you do another one?
Could I do another one? Sure. Let me add a page. Let's do one like f of x equals to, okay, I don't know. What does our library say? We could do 1 over x. F of x equals 1 over x. Draw g of x, which is 1 over x minus 2 plus 3. Okay, so that's kind of confusing, isn't it? Okay, so what are our transformations going to be? Let's start with the easy one. Do we agree that this is the easy one to handle?
Yes.
Yeah, why? Because it's outside, which means we just do what? Vertical shift up 3. Vertical shift up 3. Okay, and how about the other one? Well, what should I circle for the other one, first of all? The minus 2, right? What is that going to do to us? It's going to be a horizontal shift, and since it's negative, it's kind of the opposite of what I think. I think of positive as being to the right, but because we're inside, Okay, and inside in this sense you can think of in the following way. You can think of it like if there was parentheses here, right? Okay, so it's inside in that sense. So the horizontal shift is going to be to the right 2 units, which is kind of confusing. Okay, so let's first draw f of x. What does f of x look like? It looks like this thing, right? Okay, and then now I need to move it. I need to take all of this stuff and I need to go up 3 and to the right 2, okay? So the way I can think about that is in terms of the asymptotes, okay? So that's a $5 math word. Asymptotes refers to these lines which our graph gets really, really close to in this direction and also in really, really close to in this direction. So all I'm going to do is I'm going to think about, well, what if I were to move these asymptotes according to these shifts? So the vertical shift is going to move the horizontal asymptote up 3. Okay, so here's 1, 2, 3. So this is going to be my new... Watch this. This is going to be my new asymptote, okay, for the horizontal. And for the vertical asymptote, it needs to move to the right 2 units. So the vertical asymptote, instead of being at 0, where's it going to be? It's going to be at positive 2. So here's 1 and then 2. And we'll do another. Hello? Why can I not draw that? Okay, I'm going to move it. There we go. So these are my new asymptotes. So to draw the function, all I have to do is, let's use blue for g of x here. G of x will be shown in blue. Looks like this, okay?
So for a quiz or test, are you just looking for us to do the transformations or like the translations, not really the accuracy of the graph?
Yeah, I mean, if your graph is too inaccurate, then it's going to get to a point where it's wrong, right? So I mean, if it's not clear from your graph that you moved, you know, up 3 and over 2 or something like that. I mean, as long as you move up and right generally, and you're pretty close with the graph, I'll be happy. Okay, but let's say that you were drawing this transformation, okay, this square root one. If you drew something like this, I might take a point off for something like that because it's clear that our x-intercept should definitely not be like over here. That would be way too fast of a growth for the square root function. Does that make sense?
Yeah.
Okay. All right. Any other questions on this one? Do you like my cool dashed lines, by the way? I thought that was pretty cool. Thank you. I really feel affirmed by that. All right. So let's talk about reflection next. Okay, so how does reflection work? Well, I've taken the liberty of drawing a picture for you of how reflection works. I hope you like it. So, okay, if if this was a person. Okay, I thought you all would enjoy that. Okay, so yeah, of course, if I look in the mirror, what happens is the shape of my face gets reversed, okay, and the distance from, okay, my face to the mirror, not my face, this isn't my face, this is someone else's face, but the distance from this face to the mirror, right, is replicated on the opposite side of the location where the mirror is. So, namely, if I move the mirror further away, what's going to happen to my reflection? It's going to move away not just by the amount that we moved the mirror, but actually by double that, because what needs to be preserved is the distance here needs to be the same as the distance here, right? That's what we need. Okay, so basically, we take any point which is on the left side of our reflection, and then we are going to replicate that on the right side with the exact same distance away, okay? And of course, if we flip up and down, it's the same deal. We go from here, it needs to be the same distance away down there. Okay, so that's what a reflection is, mathematically speaking, which should correspond with the idea of having a mirror either here or here, right? Okay. So reflection about the x-axis. If we have a negative sign, okay, if we have a negative sign out front, okay, this is going to be juxtaposed with having a negative sign inside, by the way, okay? So if we have the negative sign on the outside, then what is going to happen? Okay, then the graph is going to be reflected about the x-axis. Okay, about the x-axis. So let's see an example. Well, let's start with how do we graph something like this? How do I graph something like that? Yeah, I mean, there's a couple ways. You could try to put it in vertex form, or just find the vertex and then graph from there. Or I think probably the easiest way is to factor it and then set it equal to 0 and see where the roots are going to be. So if I were to factor it, what would I get?
5 and 1.
X plus 5 and then x minus plus 1, right? And if I set that equal to 0, then I know x is going to be either -1 or -5, right? So here's -1, and then we've got 2, 3, 4, and then -5, right? Okay, so what needs to happen is the vertex should be in the middle, right? Which is, in this case, going to be at -3. Okay, and does this one open up or down? It's going to open up, right? And where's the vertex going to be? Well, if it's right in the middle, I go over 2. How much down should I go? If I go over 2, I need to go down 4, right? Okay, let me explain.
Is that factored correctly?
Did we factor it wrong? X plus 5. Oh, yeah, what am I doing? Thank you. Yeah, we should do +2 and +3, right? You all led me astray. How could you do this to me? Okay, x plus 2 and x plus 3, right? It's correct now, yes? Okay. Jeez. What have we done? Okay, that's fine. So x plus 2 and x plus 3. So where's it going to be? Not at... It's going to be at -2 and -3, right? So we're going to have a vertex at... So this is -2, this is -3. It's kind of hard to see, but I'm putting points here. -2, -3. And then it's going to look something like this, right? Okay, and in terms of what is the y value of this point going to be, is there a way I can easily tell? Yes, there is. Here's why. No, there's not, actually. Sorry. It's 1. It's 1 across here, isn't it? So I would need to move over a half, which in terms of squaring means I'm going to go down by a quarter. Right? Yes. Down by a quarter. So this is -1/4. Okay, so why is that true? That's true because if you just imagine what it would be at the origin, okay, what a regular parabola would look like at the origin, it would be at the point 0, 0. And then if I moved over by a half, okay, if I moved over by a half, and this is y equals x squared, then I square that number to get a quarter. So I know that if I move over by a half, I go up by a quarter, okay, from the vertex, right? So if I go from the vertex and I go up by a quarter and I made it to 0, then I must have started at -1/4. That's how I'm getting that number. Is that clear? That's getting confusing now. Okay, well, as long as you get the general shape right, I think I'd be pretty happy. You'd probably get most, if not all, the points. All right, so now what do I have to do? I still have to transform this guy, right? So that's what it looks like. And now let's see what it's going to look like if I am to reflect it about the x-axis. Well, I'm going to treat this as a two-sided mirror, okay? So I have stuff on one side of the mirror and on the other side of the mirror. So maybe a better thing to do would be like if it was like a surface of a lake or something like that, right? So anything that's on this side of the mirror, okay, I'm going to reflect down onto the bottom part. And anything that's on this side of the mirror, I'm going to reflect up onto the top part. Okay, so in any case, the points which are touching the mirror are not going to change. So I'm going to have something like -3, here's -2, and that's really not to scale. Let me redraw that a little bit. No, I want to move you. There we go. Okay, so it's going to look something like this. Okay, so we just flip it upside down. Okay, but the important thing to remember is we're doing this reflection with respect to the x-axis, okay, which means that anything above is going to go beneath, anything beneath is going to go above. All right, so a common mistake would be to try to draw this like, oh, I'm supposed to do a reflection, right? And so you might think, well, I'll just make it look like this instead, right? That would be kind of like a reflection. But that would be a reflection about x equals, or y equals -1/4, right? Y equals -1/4, which is not the axis of the reflection. The axis of the reflection is the x-axis, namely y equals 0, which is why it looks like this, okay? Not like this, okay? Is that clear? Any questions on how I did this reflection about the x-axis? Yep.
How do you know which one you're supposed to reflect it with, like in general, or do you like, well, I guess that
Sorry, how do I know what?
I was gonna ask, like, how do you know if we're gonna reflect it from the y to the x, but we're about to go over it?
Yeah, we're about to talk about reflection over the, okay, it comes down to this difference. Look at the difference between these two. What's the difference? Negative on the inside versus negative on the outside. So you're noticing probably a theme. When we do stuff on the outside, it always refers to the up and down world, right? When I add a number on the outside, what does it do? It moves us up and down. When I multiply by a negative number on the outside, what does it do? It flips us up and down. When I'm going to multiply by a number later, it's going to stretch us up and down. Anytime I do stuff on the inside, it's always going with the left and right, okay? With the left and right, like reflecting about the y-axis. I think of that as left and right. And then adding moves us to the right or to the left, right? Okay, does that make sense? All right, so let's see how that works. Reflection about the y-axis. Okay, so like I said, the big difference here, now the negative sign is on the inside. Okay, and this is the normal type of reflection that we think about in real life. Why? Because all of our mirrors, for the most part, are oriented vertically, right? All of our mirrors are oriented vertically, which is like a y-axis reflection. So this is the kind of reflection that you're used to. So let's see how it works with a graph. Well, if I start with the graph of f of x equals the square root of x, it looks like shown. And if I'm to reflect it, okay, if I'm to reflect it, and let's maybe put a point on here just for fun. This is the point 2, and this is the height 4. Okay, so this is the point 2, 4. Obviously not to scale. Then what's going to happen when we do f of negative x? Well, we're going to reflect where this is the mirror. So what's it going to look like? I guess that's kind of hard to describe in words. I guess we just have to draw it, huh? It's going to look like this. What's a better question is, what are the x and y coordinates going to be of this point here? It's going to be -2, 4. Okay? Well, it's going to be -2, 4. Okay, so this is reflection about the y-axis. Okay? So since we're reflecting to the left and to the right, That's why we have a negative on the inside, okay? Inside always goes with left and right. Outside always goes with up and down. Any questions on that one? Okay. Then let's see absolute value real quick. Okay, so what is absolute value going to do to one of our functions? Well, if I take an absolute value of something, what does it do? If the number inside was already positive, what does the absolute value function do? If the number inside of an absolute value is already positive, what happens? Absolutely nothing. And what is the number that we are putting inside of the absolute value? It's the y value of the points on the graph. So any of the points on the graph which have a positive y value, when we take the absolute value of it, nothing is going to happen. Okay? So it's going to look like the same for all the parts that were already positive. But when this is a negative number, when f of x is a negative number, then if I take the absolute value of a negative number, what does the absolute value sign do? It makes it into a positive by multiplying by -1, basically. Okay? So the effect that will have is it will be like a negative f of x if f of x was already negative. And if I do negative f of x, we just learned that this corresponds to reflecting about the x-axis. But we're only going to apply that reflection to the part of the graph that is already negative. Okay, so this part, what's going to happen to it? It's going to be reflected about the x-axis, right? Which means that a point down here is going to go to where? It starts in quadrant 3. What quadrant should it end up in? Quadrant 2, right? It's going to move up here. And then at this point here, right? Where's it going to move? It's going to move here, right? Okay, so at the end of the day, it's going to look something like this. Okay? Looks like a W. All right, so that's absolute value. And we're out of time for today, so that's where we'll stop. I'll see you all tomorrow. And some of you in office hours today. No, I'll go, well, okay, yeah, you can ask questions about this, but mostly I'll be going over 1.4 and 1.5 in preparation for the quiz.